Welcome everyone to the second lecture on Riemann surfaces. Athira will continue the discussion. Over to you, Athira.
Thank you, Akansha. First of all, I want to apologize for one thing that I forgot to mention, forgot to tell about one Riemann surface, which is uniformly covered by C, even though I have explicitly defined a covering for such Riemann surface. I said about uniformization theorem in which all Riemann surface which is uniformly covered by either C or Riemann sphere or upper half plane. Riemann surface which are uniformly covered by C, which has C and C star. I said about only these two surfaces. There is one more thing, all toruses. Even though I have mentioned about explicit covering map, that question map is the required covering map. Fine. Is it okay? Am I audible to everyone?
Yeah, you are audible.
Okay, fine. I will recall some result from last class. We have defined Riemann surface. Riemann surface is a connected one-dimensional complex manifold. And second thing, we have discussed here about holomorphic functions. Holomorphic functions are mapped from Riemann surface to complex planes such that F composition phi inverse is holomorphic in the usual sense for all charts U phi. Okay, and we have discussed about an important theorem, that is Riemann removable singularity theorem, on which if f is a holomorphic function on a deleted neighborhood of a point and it is bounded in some deleted neighborhood of A, then f has a holomorphic extension. In this lecture, I will discuss about holomorphic maps. Holomorphic maps between Riemann surfaces. A continuous map f from x to y, where x and y are Riemann surfaces, is said to be holomorphic if for every chart u phi on x and v psi on y, with the condition f of u is contained in this is v, and the mapping psi 2 composite with f composite with phi 1 inverse from here, let me write phi from u2 to u1 and psi from v to v1 v1. This is u. This is from v1 to u1 to v1 is holomorphic in usual sense, because this is open subset of C and this is also open subset of C. Is it okay? Is it fine?
Yeah, yes.
Yeah. Okay. Shall I describe this using diagram if you want for more clarification?
Sure.
Okay.
Yeah, it will be good.
Okay. Suppose this is x and this is y, and I'm taking open subset. This is u and some open subset here. This is v. This is our f map. And this u which is mapped to U1, and V is mapped to some V1. And this is lies in a complex plane. Okay, and this is phi. This is phi, and this is psi. We will say this F is a holomorphic map. Yeah. This is F of U. F is holomorphic if the composite map psi composite with F composite with phi inverse is holomorphic in usual sense. Fine.
Yes.
Okay. Then we'll move to very important here. Yeah.
In the definition, like why we are using, why we are demanding continuity, because differentiability, like it should imply the continuity. We don't demand in the usual sense like continuity.
In the usual sense, we don't demand continuity.
Yeah,
I
because
didn't get. Can you repeat question? Why we are?
So my question is like, why do we need this map should be continuous? Because naturally what happens, the differentiability automatically implies the way we define differentiability, or in particularly holomorphicity, it implies continuity, right? There we don't demand.
Yeah. To define holomorphicity of a function, first thing we are defining about the continuity, right? In complex analysis also, we are demanding continuity, right? This is actually a generalized notion of what we have already defined holomorphic functions on C. In there also we are telling a continuous function which is holomorphic if it has at a point, if it is differentiable in that neighborhood. We are telling about continuity of that function. We are actually finding a generalized notion. Is it okay? I don't know whether any more what we are using continuity.
I have one comment. I think you are also assuming FU subset of B. So maybe there we can use continuity to ensure FU is a subset of B.
If you find such a open subsets, we can use.
Yeah, so I think there we are using continuity.
But for that, we are already demanding that the f of u is a subset of V.
Yeah, that is guarantee if F is continuous. If F is not continuous, then it is not necessary, right?
Yeah, we can find such a neighborhood if F is continuous. Isn't it right? What you said.
Okay, fine.
Okay, we'll see. I will find out any more if what is the very necessary condition to become continuous, or maybe later you think about it. It can be define a function which is not continuous, but this definition will satisfy or not. Okay. Next, I will introduce identity theorem on Riemann surface. F1 and F2 from X to Y are two holomorphic mapping. Which coincide on a set A subset of X having a limit point A belongs to X, then F1 is identically equal to F2. Same identity theorem as in complex analysis. For this, I will consider a subset of X, set of all points in X. There exists a neighborhood W of X such that F1 restricted on this W is equal to F2 restricted on W. My idea is to show G equal to X. For that, we have to prove G is open, closed, and non-empty. By the definition itself, G is open, right? Any doubt? I hope no. So I will prove that G is closed. For that, take a point B from boundary of G, and by continuity of F1 and F2, here might be you are using continuity of the holomorphic function, isn't it? For this proof, F1 of B equal to F2 of B. Are you getting those who asked about the question? We are giving more constraint to the defining holomorphic function, that the continuity we have given that F should be continuous, that is using here to satisfy results of Riemann surface identity theorem. Is it okay that person has asked about this question? This is how we are using continuity here. Okay.
I think
Yeah.
Athira, so I think Athira, like as Nirmal was saying, yeah, I mean continuity will follow from holomorphicity, but in the definition, I think what Ravi was saying, I mean, it makes sense. Like from the beginning only, you are taking continuity so that you can find that V. I think, yeah, I mean that I think that was the reason continuity was taken in the definition. What Ravi was saying.
Yeah, might be. I think by defining about manifold, we are considering it is second countable and Hausdorff. We are giving more constraints, maybe to satisfy some theorems or all. Here also in Riemann surface, we are taking this manifold have to be connected, maybe to satisfy theorems of complex plane. Means exactly the connectedness is going to be a useful tool in proof of this theorem. Yeah.
Yeah,
Might be the
okay.
right. Yeah. Okay.
Athira, excuse me.
Yeah.
Yeah, just to add to Akansha or Ravi, yeah, Ravi is right because, like when you take your transition map as to be there, you are saying as to be, it should be holomorphic, like in the usual sense. So there you required, you are applying psi inverse F and phi, right? So there you need a
Exactly.
containment, and that is
Exactly.
where your continuity plays.
Yeah, and we need that transition map to be a homomorphism. Exactly.
Yeah, here, like the way you are defining your map to be holomorphic between the Riemann surfaces. So there you are requiring the continuity of map because at the end, whatever that transition map you are taking, that psi inverse F and phi by the definition which you wrote, there you need the containment. So that's where you are using the continuity of it.
Yeah, exactly.
Otherwise, it would be, yeah.
Fine. Thank you. To show that G is closed, yeah, I have chosen boundary point. Aim is to show that B is also belongs to G. For that, we have to find a neighborhood of B, which is properly contained in B, G. Choose charts phi from U to V on X and psi from U prime to V prime on Y, which V belongs to U and Fi of U is contained in U prime. Without loss of generality, assume that U is connected. Since F1 and F2 are holomorphic, by the definition of holomorphicity, the composite map GA, define GA psi composite with Fi composite with phi inverse from V to V prime. This is U. Is holomorphic. Since B is a boundary point, U is a neighborhood of B. This means U in the session G is non-empty and open because G both are open. Here, F1 is identically equal to F2 on U in the session G by definition of G. Then G1 is identically equal to G2 on phi of U intersection G, which is an open subset of V. By usual identity theorem on complex analysis, G1 is identical to G2 on, this is V on V. Since psi and phi are homomorphism, F1 is identically equal to F2 on U. That means U is contained in G. So V belongs to U. G is closed. Is the proof clear?
Yeah, I think, yeah, you can go ahead. Yeah.
Okay. So only remaining is to show that G is non-empty. And because A is a limit point of a set capital A where F1 and F2 are identically same, the same proof just as in the case of this case, G is closed, you can show that A belongs to G. This is a check you can show. This A belongs to G. I am leaving this. This is the same procedure I have to follow. Okay, can I proceed? If you have any doubt, we'll discuss later if we are unable to solve this. The same trick. Now I will introduce meromorphic functions. Let X be a Riemann surface and Y be an open subset. Y be an open subset of X. By a meromorphic function on Y, we mean that a holomorphic function f from y prime to t, where y prime is open subset of y such that following hold. First one, y minus y prime contains only isolated points. The second one, for every point p in y minus y prime, one has limit extending to p mod of f of x is infinity. The points in y minus y prime are called poles of f. Is the definition clear? A function is said to be holomorphic on y if we can find a open subset y prime subset of y such that y minus y prime contain only isolated point and f is holomorphic on y prime and attains infinity the points the complement of y prime on y.
Yeah.
Okay. I will denote space of all meromorphic function on y by m of y. F from space of all meromorphic functions on y. Yeah. What is that?
Hello.
Ah,
So can you please elaborate the first sentence of the definition? Can you repeat there?
meromorphic function.
Yes. Yeah. Let X be a Riemann surface and be an open subset
Oh,
of X. What does it mean?
Y be an open word of y.
Okay.
Okay. Next, I will describe a result that meromorphic function on any Riemann surface. Meromorphic function on any Riemann surface can be viewed as holomorphic map into P1. I will explain the theorem here. Let f be a meromorphic function on x. X is a Riemann surface. For each pole P of f, define f of p equal to infinity, then f from x to p1 is a holomorphic mapping. Conversely, if f from x to p1 is a holomorphic mapping, then either f is identical equal to infinity or f inverse of infinity consists of isolated points and f from x minus f inverse of infinity to c is a meromorphic function. One correspondence. Corresponding to every meromorphic function on a Riemann surface, we can extend this to, not exactly extend, we can map into P1 such that the function become holomorphic. Conversely, corresponding every holomorphic maps into P1, we can find a meromorphic function on X. Okay. I will denote all poles of F by capital P. Poles of F, where F is a meromorphic function. Since limit Z tending to P, f of z equal to infinity, f from x to P1 is continuous, we have to show that f is holomorphic. P1 is holomorphic. To check if map is holomorphic, we have to take two charts, one chart from X and another chart from P1. Chart phi from U to V on X and psi from U prime to V prime on P1 with f of U contained in U prime. We have to show that G psi composite with f of composite with phi inverse from V to V prime is holomorphic. Since f is a meromorphic function on X, that means f is holomorphic on X minus B. By the definition of meromorphic function, that means G is holomorphic on B minus phi of B. Yeah. The idea of the proof is that we will use Riemann removal singularity. Yeah. For each point, we will extend the function holomorphic to point at infinity. Poles of f. For that, here what we get, let's take this is P belongs to capital P. I am considering only for one point P. Then we have G is holomorphic on deleted neighborhood of phi of P, and also we can show that G is bounded. This is actually a check. You can use regular neighborhoods tools from smooth manifold. You can actually show that G is bounded. That means G has a holomorphic extension to V. That means F has a holomorphic extension. F is holomorphically extended to U, means contains P, holomorphic extension to B, where U is an open set. Assume one more thing, P belongs to U. Clearly, we can show that for every point in points in capital P, we can holomorphically extend F. Is the proof okay? Okay, I will proceed.
Please go ahead.
Okay. Conversely, we have a holomorphic map. F from X to P1 is holomorphic. First case, P has limit point. If P has limit point, then by identity theorem, F is identically equal to infinity. Case 2, P has no limit point, then all points of P are isolated. P has no limit point. Then by the definition of meromorphic function, F belongs to M of X. Is it clear?
Yeah.
Okay, thank you. As I have explained identity theorem on holomorphic function, same result hold for meromorphic function.
What do you mean f is equal to infinity? Because f is in P1, so what is
F is
exactly mean
identically
of f?
F is identically equal to infinity.
Yeah, but image of f in P1, so what is the relation between infinity and this element in P1?
Do we know about this space X?
Yeah, x we know
X
this.
is actually constant function.
Riemann.
F is equal to infinity means f of z equal to
Mhm.
infinity for all z belongs to X. F is a constant function because f is a holomorphic map that is given, and
Yeah,
f is f restricted to P that is equal to f of z equal to infinity for all z belongs to P, right?
correct. Yeah, but
Yeah.
image of f should be lie in P1, right? So I think it
Image of
should be say 0, 1 or 1, 0 something. Means because
image of
image of f is in contained in P1.
huh.
So I think,
This is contained in P1
yeah,
right here.
yeah. So infinity is not in P1, I'm saying.
No. What is P1? P1 is
Uh-huh.
Riemann sphere.
Oh, okay, I see. Oh, okay. Okay, that one.
I have
Okay.
actually defined this Riemann sphere and its complex structure we have defined in first class.
Okay, okay. Okay.
Okay.
Okay. Yeah, thank you.
Yeah. What was saying? Okay. Similarly, identity theorem is also hold in meromorphic function. First one, that means f and g are meromorphic function on x, and a is a subset of x. F1 coincide with g on a, then f is identically equal to g. Same trick. Proof is also very simple. If f, g are given that this is meromorphic function, that means f, g. We will use the above result from x to p1 is holomorphic function, and holomorphic map. When holomorphic map which coincide on a set which has a limit point, A has a limit point in x, then f is equal to g. Same result, same the theorem we are using here. Okay, next one is zeros of meromorphic functions are isolated, where f is a non-zero, non-zero meromorphic function. Otherwise, f become identical equal to infinity using identity theorem of meromorphic function. This space of all meromorphic function on X is a field. We are actually using the second result. If f is a meromorphic function, and one way f is also become meromorphic function. Is it okay? I will move to next section. The optimal behavior of meromorphic holomorphic functions.
Yeah, please.
Okay. Um, local behavior of holomorphic mapping. Actually, this result is very important. We can see all meromorphic functions as polynomial. Its composite map is a polynomial function like this. We will see this one. I will express. I will write the proof. I will write the theorem. Suppose x and y are Riemann surfaces, and f from x to y is a non-constant holomorphic map. Suppose a belongs to x, and I'm denoting b by f of a. Then there exists there exists an integer k greater than or equal to 1 and charge phi from q to v on x and psi from q prime to v prime on y with following properties. First one, both are centered at A and centered at B. Otherwise, yeah, A belongs to U and phi of A equal to 0. B belongs to U prime and psi of B is 0. And second condition, f of U is contained in U prime. Third one is the Lofty behavior of the holomorphic map. The map F defined as composite map phi inverse from V to B prime is given by f of z equal to z to the power k for all z belongs to V. Is the theorem clear? We are taking a holomorphic non-constant. This non-constant should be marked. F is a non-constant holomorphic map, and we can for each point A in X, and we are taking its image B as f of A. We can find a two charts which is centered at A and centered at B, and its local behavior. That composite map actually looks like Z mapping to Z to the power K. I will draw this. This is U and U prime. U prime. This is mapping to this is our A and this is our B. That is F, phi, and psi. This A is mapping to 0 and B is also mapping to 0. This is the map psi composite F composite with phi inverse. This is mapped to some open subset of 0 to open subset of 0. Okay. I will go to the proof. First one is clear, right? Second one is by continuity, and first one is by, if you take any chart, we can translate the chart by phi minus phi of A to make it so that this will map A to 0. This is by continuity. Proof third one. Since small f is not constant, our capital F become not constant. First, I will choose charts. Phi from U1 to V1. Later, I will redefine phi 1 to be phi I have to do some calculations. First, I will take a chart phi 1 and another chart on X where A belongs to U1, psi from U prime to V prime. And F1 is defined as psi composite with F composite with phi 1 from V1 to V prime. This is non-constant. Since small f is holomorphic, this is also holomorphic. And F1 of 0, which is mapping to 0, because here 0 is image of A and which is mapping to B, and B here mapping to 0. That means F is mapping 0 to 0. Here F1 is a holomorphic function on complex plane. So it has a power series expansion. F1 of Z equal to Z to the power K G of Z, where clearly K greater than equal to 1 because this satisfies this condition, and G of Z is non-vanishing holomorphic function on some neighborhood of 0. Here I will call this neighborhood as W. Let it be W. Okay. Then there exists a holomorphic function H from W to C star such that H of Z D to the power K is, that is kth root of G of Z exists. Is this argument clear? Can anyone tell about idea of this argument? Existence of kth root of holomorphic function G.
Yeah, G is non-vanishing and locally it's simply connected domain, so we can define the logarithm.
Yeah, exactly. So we can write F1 of Z as, since F1 of Z is set to the power K G of Z, so we can write like this. And define alpha from W to means, yeah, maybe this will make problem. I will write alpha of Z as Z times H of Z. Claim is alpha is a biholomorphism from an open subset of B1 containing 0. Alpha, I am finding the derivative of alpha, which is H of Z times Z times H prime of Z, and alpha prime of 0 is H of 0. This is non-zero. Can I say that alpha has a inverse?
Yeah, using inverse function theorem maybe.
Yeah, using inverse function theorem. This alpha is a holomorphic. Clearly, this alpha is a holomorphic map injectivity, and it's actually biholomorphic in some neighborhood of 0. Okay, then we done with our claim. Alpha is a biholomorphism from some open subset of 0. I am writing that open subset as V2, and this is mapping to V, and V is called alpha of V2. It's a biholomorphism. I will write B as inverse of alpha. Then we will replace our phi 1 from U1 to V1 by chart phi from U to V, where phi is alpha composed with phi 1, U is phi 1 inverse of V2. I will explain with diagram. Here, alpha is a map from V2 to V. This is contained in V1, and phi 1 is a map from U1 to V1, and I am taking phi 1 inverse of V2, that is U from V2 is map into V by alpha. Composite in this map, I get phi. Is the map clear? We are almost done. Okay, then I am defining f of z as f composite with psi composite with f composite phi inverse of z. That means this phi is alpha composite with phi 1, psi composite with phi 1 inverse of alpha inverse of z. Here, alpha inverse is beta. I will replace this with beta. Beta of z. We have already, this is our f1, right? f1 of beta of z. We have already showed that it has an expression beta of z times h of beta of z to the power k. We have just observed here. Yeah, here. So, since alpha of z is z times h of z, I can write it as alpha composite with beta of z to the power k. Since beta is alpha inverse, this is z to the power k. We are done. Local behavior of holomorphic function. Composite maps actually a polynomial. Any doubt? This K is actually called multiplicity of model. I will explain what is multiplicity. Multiplicity of a holomorphic map. F from X to Y is a holomorphic map, and let A belongs to X, P equal to F of A. For every neighborhood, U naught of A, the exists neighborhood U subset of U naught neighborhood of A and neighborhood W of P such that cardinality of this set is K. For every Y belongs to W minus P. Then this K is called multiplicity of F at the point A. You can actually look this in the case of Z map to Z to the power K. If you take here A is 0 and B is also 0. If you take any point, if I'm taking it's as 1, I can find for every Y, I can find nth root of unity. Means kth root of unity, K3 images. This is actually called multiplicity. May I see? You can also check with example f of z is a polynomial of type ck, which of degree k. Then by redefining f of infinity equal to infinity, f of infinity is mapped to infinity, f from p1 to p1 is holomorphic. Multiplicity of f at infinity is actually k. This you can check using charts of infinity in Riemann sphere. Actually, just look this one. Psi composite with f composite phi inverse. You can actually use this result here. We have observed the value of k from f1 itself. By finding the composite map from the composite map itself, we can actually find the multiplicity. We don't have to do all the proof. The same trick will help to find the multiplicity of infinity for this polynomial. I will skip this exercise. As in complex analysis, here also non-constant holomorphic map is an open map. This is actually corollary to the above theorem. Up to this is okay. Any questions?
Yeah, it's okay.
Okay, fine. So this, suppose x to y is the holomorphic map and use open subset of x. Our aim is to show that f of u is open. This is our claim. Here I will prove with chart. I am assuming that use a chart. Remaining we can prove using the same technique. For p belongs to f of u, choose charts p prime psi at p such that f of u is contained in u prime. Here u prime is a chart. Then by above condition, above theorem, third property, f of z, the composite map, is a polynomial of this type. This is a holomorphic map, and which is open, and f is that means this f is open. If you take write this phi from u to v and psi from u prime to v prime, f of v is psi composite f composite with phi inverse of v. This is actually psi composite with f of u. Since psi is a homeomorphism, it means f of u is open. Is it clear?
Yep.
Okay. Here I proved this theorem by taking u as a chart. If u is not a chart, then find a chart which containing. Yeah. If u is not a chart, then find a chart which contains the point. F of we are taking b, right? A belongs to u, then find chart v contained in u and do the same procedure here. Corresponding chart here, and we have to show the same. And we will end by showing that f of v is completely contained in, it's an open subset of f of v. Is it okay?
Yep.
That means okay. And one more corollary. Injective holomorphic map is a biholomorphism, biholomorphic map onto its image. Same theorem in complex analysis here. Here actually we are using the local behavior of the holomorphic function. We know that the composite map is look like composite map of cap small f is look like z to the power k. Already given that holomorphic map with f is 1 1. That means multiplicity is 1, k is 1. Is it? Psi composite f of phi inverse of z is z. Isn't it?
Right.
Yeah. That means f is invertible and f inverse, because these charts are holomorphism, f inverse is also a holomorphism. So f is biholomorphic onto its image. These are the theorems analogous to theorems in complex analysis. One more thing, maximum model principle. Maximum principle. Suppose f from x to c is a non-constant holomorphic function, then the absolute value of f does not attain its maximum. This is also very easy proof. Suppose a mod f has maximum at some point a belongs to x. A belongs to x. Then I'm denoting this capital R by mod fa, which is supremum of all set of mod of f of x, where x lies in Riemann surface x. That makes our f of x, which lies on the disk node of less than or equal to, since f is an open map and f of x is open, so f of x is completely contained in interior of k, which is a contradiction because f of a belongs to boundary of k. So f does not attain maximum. Is it fine? Okay,
Yeah.
I'll move to next. Yeah, next here. All holomorphic maps on compact Riemann surface is surjective. X and Y are Riemann surface, and here X is compact, and f from X to Y is a non-constant holomorphic map. Then Y is compact and F is surjective. This proof is also very simple since X is compact, and actually this theorem will help to categorize all holomorphic function on a compact Riemann surface. X is compact, that means f of x is compact. Since the y is Hausdorff space, f of x is closed. Since holomorphic map is open, f of x is open. Since y is connected, and so f of x is equal to y, and y is compact, and f is surjective. Clear, right? Three-line proof. Nothing. Okay. Yeah. All non-constant, all holomorphic function on compact Riemann surface is constant. We will use the above theorem. Compact Riemann surface are constant. If f is non-constant and if f is non-constant, then by above theorem, f is surjective. That means f of x is c. And also f of x is compact, c is compact. This is a contradiction. So f is constant. This is also clear, right? Just simple check.
Yeah.
Yeah. Next, I will categorize all meromorphic function on Riemann sphere. May I proceed? I am already 6:2. Shall I explain this?
You can take 5 more minutes.
Okay. Thank you. Correct. Every meromorphic function f on P1 is rational. We have classified all non-constant holomorphic function on compact Riemann surface, which are constant functions, and we can classify all meromorphic function on P1, which are rational functions. Actually, this functions will be used to construct branched covering of P1. Branched covering of P1. Yeah, exactly. This type of corresponding to this type of functions. Let P equal to set of all poles of F. I'm denoting these poles by A1 to AK. This is fine because of identity theorem. And if infinity belongs to P, I will replace F by 1 by F. So I am assuming that replacing F by 1 by F. With the clause of generality, I am assuming if F is if we can show that 1 by F is rational, then F is also rational. No change occurs. So I am assuming that infinity does not belongs to P. Okay. Given that f is a meromorphic function, so consider the principal part of Lorentz expansion of f. Consider the principal part of Lorentz series expansion of f at aj for each aj in P. I am denoting this by hj of z. Tij z minus aj. This is a to the power j, the j from minus ni to minus 1. Yeah. Then I am defining g as f minus all the principal parts. Eliminating all principal parts. Then this G is holomorphic on P1. Is it clear? By eliminating all principal parts from F, this become holomorphic.
Yeah.
Okay. We have already said that holomorphic function on compact Riemann surface is constant. That means G is constant, which gives F is rational, because these functions rational functions. Rational means polynomial by another polynomial. Is it fine? This proof?
Yep.
Yeah. Okay. Next, I will give a very quick proof of Liouville's theorem and fundamental theorem of algebra. We have so many theorems of fundamental theorem of algebra. Using tools in Riemann surface, we can also prove that. Let me do it here. This will take few minutes, very few minutes. Liouville's theorem. A very bounded holomorphic function f from C to C is constant. By Riemann removal singularity theorem, f has a holomorphic extension to P1. Since a holomorphic function is clear, I have a holomorphic function f from C to C, and C is a deleted neighborhood of, I can consider this from P1 to C, right? C is a deleted neighborhood of infinity, and f is bounded on that neighborhood. So f has a holomorphic extension to infinity. That means f from P1 to C is holomorphic. Holomorphic function on compact Riemann surface are constant. So f is constant. Is it clear?
Yeah.
Yeah, fine. Next is fundamental theorem. Most eye-pleasing proof in this section. Fundamental theorem of algebra. Let n greater than equal to 1 and let f of z is a polynomial where CA belongs is a complex numbers, then there exists at least one point A in C such that f has 0 at A. By defining f at infinity equal to infinity, we get a holomorphic map from P1 to P1, which is holomorphic. We have showed in previous result that a holomorphic function on a compact set is surjective. So for 0 belongs to P1, which has inverse image, there exists A belongs to P such that f of A is 0. F is surjective, we have already shown. Is it okay?
Yeah.
Yeah. Any doubts?
Does hello? Does anybody have any question? Okay, then let's thank the speaker. Thank you, Athira, for the lectures. So
Thank you, Anusha.
yeah, so we shall continue the discussion on Riemann surfaces. Our next speaker in the series will be Abhishek. So see you all in the next week. Thank you, Athira.
Thank you.